Welcome to this week's Udacity Deep Reinforcement Learning Nanodegree weekly webinar. This week I'm going to be focusing on Alpha Zero. Now Alpha Zero has come from DeepMind and was after AlphaGo 0 and then Alpha Zero. Basically AlphaGo was the first, which I'll talk about a bit, defeated the Go champion, which was thought would be 10 years away. Alpha Zero was able to beat AlphaGo in only 2 to 4 hours of training. So it's an incredible algorithm for classic games, and will give you a real understanding of the power of when it can use multicolored tree search and other features. So before I go, I'm going to go on to what we're going to say. First, I'm going to go on about AlphaGo to Alpha Zero, general game playing DFS, multicolored tree search, upper confidence bounds applied to trees, deep learning heuristic functions, and Alpha Zero, the big picture. So, AlphaGo. If you're following the AI world, you've probably heard about AlphaGo. The ancient Chinese game of Go was once thought impossible for machines to play. It has more board positions that didn't actually come up properly than basically the atoms in the universe. Top grandmasters regularly trounce the best computer Go programs and observe 10 or 15 stone handicap, justifying their decision in terms of abstract strategic concepts. Jasinski, Pasecki, Senti, Tanuki balance they believe computers would never be able to learn. Well, they thought. Demis Hassabis and his team at DeepMind believed otherwise, and they spent 3 years, painstaking years, trying to prove this disbelief, collecting Go data from expert databases, tuning deep neural network architecture, and developing hybrid strategies honed against people as well as machines. Eventually, their efforts accumulated in a dizzyingly complex strategic program they called AlphaGo, trained using millions of hours of CPU and TPU time, able to compete with the best of the best Go players. They set up a match between AlphaGo Grandmaster Lee Sedol, and the rest is history. Now, if you haven't watched the documentary AlphaGo, highly recommend watching it. Fantastic, one of my best favorite AI docos, which there isn't that many, but it's pretty damn good. Now, AlphaGo to Alpha Zero. Now, but I'm not talking about AlphaGo here. Here, I'm here to discuss Alpha Zero and the algorithms some DeepMind research was released a couple of years ago. The algorithm that uses no previous information or human played game whatsoever, starting with nothing but the rules of the game. The algorithm that was able to handily beat the original version of Go in only 4 hours of training time. The algorithm that can be applied without modification to chess, shogi, and almost any other classical game with perfect information and no random elements. If computer programs could feel humiliation, Alpha Zero would be making every commercial AI chess or Go program overload with shame. Every single one of them, including the original AlphaGo, uses a ridiculous large pre-computed table base of moves, professional databases of well-played games, and carefully crafted heuristic functions with tons of hacky edge cases. Improving these programs required eking out more efficiency from the underlying hardware and make tiny but arcane changes to various interlocking factors and scores. Alpha Zero saw the cutthroat, hyper-competitive ecosystem of competitive game playing forged through hundreds of thousands of hours of programming efforts and watered with blood of millions of slaughtered chickens, and decided that it was a problem worth spending just 4 hours on. That's got to hurt. And to add insult to injury, AlphaGo is a radically simple algorithm. It's so simple that, like me, you should be able to explain it and teach you how to code it. At least that's the idea. General game playing and DFS. In game theory, rather than the reason about specific games, mathematicians like to reason about special class of games, turn-based, two-player games with perfect information. In these games, both players make everything relevant about the state and game at any given time. Furthermore, there are no randomness or uncertainty how making moves affect the game. Making given moves will always roll in the same final game state, one that both players will know with complete certainty. We call games like these classical games. Here's a sample of some classic games: tic-tac-toe, chess, go, gamoku, and mancala. But games like poker, rock, paper, scissors, the Prisoner's Dilemma, and video games like StarCraft don't, because they have hidden states and random state changes. General playing games in DFS again. When games have a random element and hidden state, it's much more difficult to design AI systems to play them, although we have been powerful poker and StarCraft AI developed. Thus, AlphaZero is restricted to solving classical games only. In the classical game, because both players have perfect information, every position is either winnable or unwinnable. Either player who is just about to make a move can win, given they choose the right move, or they can't, because no matter what move they make, the game is winnable for the other player. When you add the possibility of drawing, any of the player wins, and there are three possible values for a given state. Either it is a guaranteed loss, a guaranteed win, or a guaranteed draw. If the definition makes you shout recursion, then your instincts are the right track. In fact, it is easy to determine the value of a game state using a self-referential definition of winnability. We can write some Python code using a predefined abstract game class. Note that we handle the game using general methods such as make, move, undo move, and over, and could apply to any game. So as you can see here, we're importing what we need, so games, tic-tac-toe from games, chess games, and gamoku games. We defined a function here. So if games dot over, return game score, you've got the state value, and then we've basically got a loop that goes, makes a move, you do a move, state value dot append, and game undo move. Now that you can create an AI that always chooses the best move, we simply tell the AI to pick a move that results in the lowest resultant score for the opponent. We call this DFS approach because to choose a move, we have to do depth first search on the tree of possible game states. So the AI best move, action dictionary for move in games or valid moves, make a move, action dict, and value, and then undo move as well option. General game playing and DFS. In fact, simple AI can play tic-tac-toe optimally. It will always either win or draw with anyone it plays. So does this mean that we've solved all two-player classical games? Not quite. Although the recursion above looks simple, it has to check all possible game states reachable for a given state in order to compute the value of the state. Thus, even though there do exist optimal strategies for complex games like chess and go, their game tree are so intractable, large, that it would be impossible to find them. The reason for the slow progress in DFS is that when estimating the value of a given state in search, both players must play optimally, choosing the move that gives the best value requiring complex recursion. Maybe instead of making the player choose optimal moves, which is extremely computationally expensive, we compute the value of a state by making the player choose random moves from there on and seeing who wins. Or perhaps we could even use cheap computational heuristics to make the player more likely to choose a good move. Monte Carlo tree search. This is the basic idea between Monte Carlo tree search. Use random exploration to estimate the value of the state. We call the single random game a playout. If you play 1,000 playouts from a given position, player 1 wins 60% of the time. It's likely that the position X is better for player 1 than player 2. Thus, we can create a Monte Carlo value function that estimates the value of the state using a given number of random playouts. Observe how similar this code is to the previous DFS code. The only difference is instead of iterating through all possible possibilities and picking the best one, we randomly choose one. As you can see, player, return value. Find the expected value of the game by running a specific number of random simulations. Choose the best value move to play using Monte Carlo tree search. Monte Carlo search with sufficient number of random playouts, usually a thumb, can be surprisingly good results on many simple games, including the standard tic-tac-toe. It is also extremely easy to fall a Monte Carlo based IO. To see this, we're going to have to scale up significantly more complicated games. Gamoku and Gamoku, you win by getting 5 by 5 rail pieces on a 19 by 19 board, which some positions might be easy to win with against a random opponent. They're utterly undefensible against a competitive opponent. Upper confidence bounds apply to trees. One way to fix this problem is to make the move selection within the playout be more intelligent. Rather than having move choices within the playout to be random, we want the opponent to choose their move using some knowledge of what moves are worth playing. This is superficially similar to what we decide inside our DFS method, where we experimented with every possible move and choose the move with the highest resultant value. Since computing the true value of a move would be extremely expensive, we instead want to compute a cheap heuristic approximation, heuristic value of the true value of each move and choose moves within playouts based on this heuristic. For the perspective of the algorithm, each move in the complete black box is its value unknown, almost like a slot machine with unknown payout probabilities. Some moves might have only 30% win rate. Other moves could have a 70% win rate. Crucially, you don't know any of this in advance. You need to balance testing the slot machine recording statistics, actually choosing the best move. That's what UGC algorithm is for, balancing exploration and exploration in a reasonable way. This is a great upper confidence bounds applied to tree UGC. Thus, we define the heuristic value here, where S is the aggregated score after playing move I in all simulations thus far, NI the number of plays of moves in all simulations thus far, N the total number of games states simulated, and C an adjustable constant representation, the amount of exploration to allow. The first term in heuristic encourages exploration, playing known moves with higher values, and tends to result in victory. The second term encourages exploration, trying out moves that have low visit counts and updating statistics so that we have a better knowledge of how valuable and useful these moves are. Where the previous two algorithms we worked with, DFS and MCTS, were static, UCT involves learning over time. The first time the UCT algorithm runs, it focuses more on exploring all game states, with the playouts looking more like a Monte Carlo tree search. But as it collects more and more data, the random playouts become less random and more heavy exploring moves and paths that have already proven to be good choices, and ignoring those that haven't. Use the statistics collected during simulation about good and bad states to inform how to compute the winnable of states. This helps it improve further in self-reinforcing cycle. So, this is the code shows a simple version of UCT in action. Note, in order to compute moves in a reasonable amount of time, you'd only want to parallelize the code to run playouts asynchronously. You can see my efficient multi-thread implementation of USD here. So, as you can see, basic value, record, playout value, Monte Carlo value. A bit of a look through. A key component of success of UCT is how to allow the construction of lopsided exploration trees. In complex games like Chess Go, there are incomparable large number of states, and most of them are unimportant because they can only be reached if one of both players plays extremely badly. Using UCT, you can avoid exploring out these useless states and focus most on your computational energy on simulating games in interesting portions of the state space, as the diagram below shows. Deep learning heuristic function. Given enough playouts, UCT will be able to explore all of the important game positions in any game and determine the value using Monte Carlo method. But the amount of playouts needed in games like Chess Go and Gamoku for this to happen is computationally infeasible, even with UCT prioritization. Thus, Viable Monte Carlo tree search engines for these games end up exploiting a lot of domain-specific knowledge and heuristics. To see why, look at the diagram below. The first and second Gamoka games are completely different in terms of position of pieces, but essentially components of the situation are the same. Difference in piece location structure, most relevant strategically. Yes, to the UCT algorithm, the two games represented different states. Even if UCT has thoroughly explored game 1 and knows that it is 0.2 advantage black, it has to start from scratch when exploring game number 2. Humans have no problem noting the similarities between different game positions and intuitively noting the similar strategies should apply. In fact, rather than memorizing different game states, we tend to do this by default. How can we train AI to do the same? The key is learning to use deep convolutional neural network, DCNNs, and fuzzy stores of values. Previous research has shown that DCNNs show success at a wide variety of image tasks, including image classification, scene reconstruction, handwriting recognition, and much more. Crucially, DCNNs are able to learn abstract representation of images after being shown a few thousand divers' photos of cats. For example, they can learn to classify cats or any other angle, location, or color. Instead of memorizing a heuristic value for every game state we encounter and putting it in hash table, we can train a deep neural network to learn heuristic values from images of board games. The network will remember previous states fairly accurately, assuming we train the DCNN well, but it will be able to generalize to new, never before seen games. Sure, because DCNNs are a learning algorithm, predicted values of states would never be perfect, but that's okay. We're just using them as a fuzzy heuristic in the search algorithm anyway. All our previous methods were based on exhaustive playouts. Adding in deep neural network gives our model more of the learned intuition that human players often leverage. So, here's some code that creates a simple DCNN in PyTorch using TorchTrain library to enable Ionic data loading designed to predict the value of a given 19 binary Gamoka state in Gamoka. Now, we can modify the record and heuristic value function to make them train and predict with the neural net respectively. After only 2 days training with algorithm, we can achieve near optimal play, followed by double victory on 9x9 Gamoka. Using deep learning really does cut down the search time and improves the generality of standard Monte Carlo tree search significantly. It turns out it's really all there is to for AlphaZero algorithm, except for a few computational implementation details. The neural network architecture used was extremely deep, inspired by ResNet, which has seen great success on ImageNet and other related computational vision tasks. AlphaZero uses a lot of tricks from the computer vision toolbox, including aggressive data augmentation. Along with predicting the value of a given state, AlphaZero also tries to predict the probability distribution of the best moves from a given state to combat overfitting using a network with a policy head and a value head. These two measures cross-validate one another to ensure the network is rarely confident about wrong predictions. AlphaZero uses a crazy amount of playouts, 800 simulations per move, and self-play, 100,000 games to learn its value function. Here's a bit of a look at it. There's policy head, residual layer, value head, and the network. So why has AlphaZero been so ridiculously successful in so many different domains, given that it's just a straightforward combination of Monte Carlo tree search and UCT with a recent deep neural network research? Some researchers argue that the main strength of AlphaZero was its compute time. The research paper claims that AlphaZero only trained for 4 hours, but it's important to note this is 4 hours of training on Google's most advanced hardware. It provides tens of processing units, or TPUs. Google claims that its TPUs are at least 100 times as fast as the highest-end GPUs and based on exploration like thousands of times faster than the hardware available 2 or 5 years ago. Thus, his very real sense it might have been impossible to create AlphaZero before 2017. The technology just wasn't there. In fact, if you aren't Google, it might be impossible to create AlphaZero now, given that many failed incomplete replication attempts, Lila Zero, Rock AlphaGo. From that point of view, the AlphaZero success is more the success of Google's hardware development team. But even if it's difficult to implement on anything but the fastest hardware, AlphaZero design is still brilliant conceptually, certain much more elegant than the brute force algorithms that used to dominate the top level chess and Go play, and can provide inspiration for new types of self-learning algorithms. As the deep neural network improves, it makes the Monte Carlo tree search more efficient, which results in better state validation to train and deep neural networks, with causing a self-reinforcing cycle that can be quickly snowballed. Ultimately, the development of AlphaZero is bound to cause a lot of reverberation in the AI community. Early in the post, I discussed how shocking AlphaZero's development was, and its point I'd like to reiterate. Nobody expected that it would be possible to beat the very best chess and Go engines without any domain knowledge using such an elegant, simple, general-purpose algorithm. Nobody could expect it to have happened soon. Now it seems like all classical games, simple enough for humans to play, are also simple enough for computers to solve. What will be the next field that AI eats? Now, I have a Q&A. If you've got any questions, let me know now. Okay, no questions. But thank you very much for this week's Udacity Deep Reinforcement Learning webinar, and I'll see you guys next week.